Let us now apply our concept of mass transfer coefficient to a old friend, which is Equimolar counter-diffusion. If you don't remember what we're talking about, definitely go back to Fick's law, molecular diffusion, and go and find out the Equimolar diffusion case, in which essentially what we are having here is two components that are interacting between each other. They are equimolar, meaning that for every mole of A that goes to the right, every mole of B will go to the left. Therefore, we have this interesting concept in which the molar flow rates or molar fluxes are the same for A and B, of course in opposite directions. You can either state these opposite directions, or if you're using a reference or frame of reference, use the negative sign. No bulk motion contribution to the flux, meaning that we are not accounting for the velocity of the flow rate. And this will facilitate a lot the equation. So this is just a review. If you already know, let's go to the hardcore calculations. As stated before, this is true. This part right here is something I haven't presented to you because I don't think it's that important. But if you see this, I think it's a psi. It's nothing more than the, let's say, the fraction, or this appears a lot is in the molecular equation, is the fraction either for a binary system or ternary system. But what happens here is that you get the flux of A divided by the total flux, which will be A, B, C, and D, and so on. In this specific case, you will see that because the flux are negative, you get this part right here as 0. Therefore, it's undefined, making this specific case very unusual, or let it be a very easy case for us, which is the equimolar counter-diffusion. And if you were to calculate that of unimolecular diffusion, you will see that actually this will be equal to 1, because this will be equal to 0. Well, actually, let me write it very fast for you. And because NB is stagnant, this is equal to 0, and what you get is 1. And as you can imagine, you can also have 0, which will not make that much of sense. That specific case will imply that there is no molecular diffusion whatsoever. So 0 is no molecular diffusion, 1 will be unimolecular diffusion, undefined will be this specific case, equimolar counter-diffusion. And if you don't remember, guys, but remember that you should by now, that the molar flux of A must be equal to the molecular diffusion flux. That is, we are ignoring all the bulk phase as stated here. Yeah, bulk motion contribution is ignored. So remember this little part right here equals 0. And in this case, then, molar flux of A equals JA, which we know JA is always equals to Fick's law, which developed in its simple case will be the difference of concentrations in the path of mass transfer and the coefficient for diffusivity. So far, we already know that we have the expression for concentrations, for molar composition, and for partial pressures, depending on what type of units or phases you're using. If we apply this to the liquid-gas interface, which we know it's very common in our industrial applications, we will get several cases. This is the generic one. And as you can see here, guys, I'm using a lower subscript, L for liquid phase, G for gas phase. So that will be, this is the gas phase, this is the liquid phase. Now we're going to model this path number 1 and this path number 2. The first one that we're going to model is L, so we must be in this part. This is L. So I'm going to assume right now that, well, I don't want to use that much variables, so let it be, this will be the origin, and this will be, this will be C1, and this will be C2. What you will see is, of course, we cannot use partial pressures, because we're talking about liquids, so mostly our study remains either in concentrations, difference in concentrations in the path, times the coefficient, or molar fractions, which is essentially the same. We just took out concentration out of the equation, which is right here. Remember that this concentration can be the total concentration of our species right here. Now we're talking about gas. This is a little bit more interesting because we can now use partial pressures. Now we will be talking about this range right here. And the difference will be, well, here talking about concentration alone. This is gas concentration, not liquid concentration. But look at this and this, they are pretty similar. So it's very important to differ then the points. In this case, I'm separating the cases. Let's say that they are not in the same position, but the best case scenario will be to assume C0, C1, and C2. And if this is true, then I will need to account for the difference in the gas, C1 minus C0, and the difference for the liquid, C2 minus C1. And the total length will be C2 minus C0, which of course doesn't make that much sense, other than it will be the total length between the gas phase or the bulk phase of the gas and the bulk phase of the liquid. For now, I just wanted to let you know that the flux of A in the gas phase and the flux of L in the gas phase, liquid phase, can be modeled as follows. And of course, you don't need to assume that these are the same, even though some cases you can still assume it is true. Now, an important thing I want to show you is that whenever we're talking about molar fractions in the liquid phase, I will be using X. And when I use vapor phase, I will be using Y. Now, I'll remember that the main task of this section is to force the mass transfer coefficient in equimolar counter-diffusion. And if you don't remember what was the main idea, is essentially I want a mass flux or a molar flux with the mass transfer coefficient multiplying a difference of driving force. And of course, I have my driving force in concentration in the liquid phase and molar fraction in the liquid phase. Therefore, these will be always constant, and this will be always constant. So hopefully you get the idea what we're doing here. For the gas phase, remember driving force can also be partial pressures, molar fractions, and concentrations. So what I did here is, once again, I'm taking away these constants. And of course, I'm not saying that delta C or the change in pathway will be different, but once you fix the system, this will always be constant, and the only thing that will change is the concentration. And what I will do is, well, take this one here. I will assume that the diffusivity of A in B divided by the difference in Z value, which is the pathway or the total path length of the mass transfer, and the negative sign, I'm going to include it here, as you can see here, A2 minus A1, this is A1 minus A2. I will call this KL, the mass transfer coefficient in the liquid phase. And this is the same, what I'm doing exactly, negative goes inside, and this will be my mass transfer coefficient. And for the gas phase, I do the same. So what you can see from now, guys, is that there are a lot of coefficients depending on what type of units you're using, what phase you are modeling. So liquid phase, gas phase, and if so, either concentration, molar fractions, or partial pressures. And right now, I will use K apostrophe for equimolar counter-diffusion, because as you can imagine, when we go to unimolecular diffusion, I will be using K alone. And why is this? Essentially just because in most books, you will encounter that whenever they try to apply the mass transfer coefficient to the unimolecular diffusion case, well, they use K and then they continue with equimolar counter-diffusion. But I prefer to start with equimolar counter-diffusion because it's very straightforward. You can see the coefficients very easily. And as you can imagine, the coefficients can be converted between each other. Kj times P will give you Ky and Kx. Remember always to use the apostrophe. And the only thing that we are changing from here, this is fractions, these concentrations, partial pressures, and so on. Also, you can encounter Fg and Fl, which later on are going to be defined. But for now, as you can imagine, here is literally Fg equals K apostrophe Y, and Fl equals K apostrophe X. And this is what I wanted to show you on this lecture, equimolar counter-diffusion. We have a lot of equations. This will be one, this will be another one, two equations for the liquid phase. 1 for the gas phase 2 and 3. Special notes, this is valid at low and high concentrations, meaning that we can apply this to dilute cases and non-dilute cases or concentrated cases. The problem right here is that the mass transfer rate gotta be low in order to this be valid. Remember, mass transfer or diffusivity, we assume that the bulk flow contribution must be low, meaning that the velocity of the bulk must be low. So we can apply molar flux of A equals to molar flux of A according only to molecular diffusion. And let's continue now with some problems.